Let's start. So currently we are learning about the loop structure using the branch equal, branch not equal, and comparison operation like a set on less than or set on less than immediate. Okay, so this exercise 3 is representing the nested loop. So I think you can do the translation for this nested loop using the MIPS code. So for instance, for the first loop case, you're just assigning 0 value in the sum register and then doing the comparison using some set less than I instruction 100. So it will be storing 2. If this is false, then we have to be exiting from the loop, right? So if branch, if this is equal, that means 0. So $2 is 0. In the case, we are going to the exit for the outer loop. And then we are doing the inner part. So inner part, it has another loop structure. So we have to do initialize some another register. And then comparing the two registers. So set less than, we are comparing J and I. So J is $2, I is $1, $2, $1, and $3, right? This is $3. And the result is stored in the sum register. Okay, and then branch equal or branch not equal, which one do you have to use for this $2, $0, and exit 2? So what do you have to do? So $2 is $3 is representing J, $1 is representing I. So J is less than I. Then we have to stay in the loop. If it's false, then we have to leave from. Okay, so it is equal. So J is less than I. That is false. Then we are leaving from this inner loop. And then here, this is another if statement, right? So to do that, what do we have to do? We have to do J modulo 4. So how can we compute J modulo 4? So we didn't know what the division or modulus operation yet, right? But we can do this modulo 4 case. How we can do that? Modulo 4 means we are just looking if in the binary. In the binary, something is happening. The last 2-bit is representing mode 4 value, right? So we just need to taking the last 2-bit. Okay, so mode 4 means last 2 bits. Okay, mode 2 means we are just looking at the last bit only. Mode A means we are looking at the last 3 bits. Okay, so in that special case, we can compute this last bit or compute this modulus using the simple operation. So how can you compute the last 2 bit only? How we can extract this last 2 bit? The simplest way is using AND operation. AND operation. So what bit do we have to apply? Something, 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 and 0, 1. In this case, what we are doing applying is AND 0, 0, 0, 0, 1, 1. Okay, so then the every part is 0. And last two part is depending on the input value. Okay, so 0, 0, 0, 0, 0, 1, 1, that is actually number 3, right? That's 3 in hexadecimal. This is binary. So simply what we have to do is computing j modulo 4. That is actually same to the add, not the add, and I, j is 3, and modulo 4 is 3, and okay. So that means $4 is $3 and 3, which is, this is extracting last 2 bit. Okay, so AND operation is much faster than division operation. So if you can avoid division operation, then you have to use that operation. Okay, so if you can avoid the multiplication or division using some logical operation, then you have to use that operation. Okay, so $4 is containing the j modulo 4, and then we have to comparing these two values. So in order to do that, we have to comparing the constant value 3. Okay, so we have to compare. Comparing is equality check. So we just need to branch equal, branch not equal, right? Branch equal and not equal. $4. And it should be constant 3. And continue means it is continuing to the inner loop, right? So here out loop and here inner loop. Okay, so this should be going to the inner loop. Okay, but we cannot specify constant value here. So constant value should be stored in some register. So $5 is containing constant 3. So we are specifying $5 here. Okay. So comparing the $4, that is modulus operation result, $5 contains the constant value 3, and this is equal, then are we going to the inner loop, right? So here, what condition do you have to give? Equal or not equal for this branch? Yeah, it is equal. So $4 is equal to the $5. So equal case, we are jumping to the inner loop. Okay, so no p is there, and no p is there. Operation, and then j s is increased. So add j will be $6, $6, and j is $2, $3, right? $3. Okay. And then last one is also another if statement. Okay, so what this meaning is, s is larger than 1024, then we are breaking, right? But this is greater than, we just know about the less than, right? So here 1024 is less than s. But the first should be register name rather than constant value. So for that one, we have to call set on less than instruction and comparing s. S is $6 and 1024 should be specified someplace, but there is no 1024. So you have to set in 1024 in some register. $7 is containing 1024. Okay, so here $7 and result is containing in the $2. Okay, if this is true, then we are breaking. Breaking means where do we have to go? The break means we are going outside of the inner loop, right? Outside of inner loop. Okay, so that is actually exit 2. Okay, so we didn't specify exit 2 yet, but there is exit 2. Okay, so which one do we have to give here? Branch equal, not equal? Okay, so here, this is true, then it is break. So that means it is not 0, then break. Okay, and then no operation. Then the closing of the inner loop. Closing of inner loop means that we are going back to the original loop, right? So here we have to give jump inner loop, no P. Okay. And then what do we do? Actually, there is another loop closing, outer loop part. So for the outer loop, we have to jump out loop and operation. Okay. So inner loop is from this loop to this part. Okay, so this is inner loop. So outer, the inner loop, our exit part is here. Exit 2. And then the outer part, exit. Here. This is the outer of the loop structure, our loop structure. And we need to initialize the S. So add I, S is $6. $6 is initialized. Okay. Okay, so then can you write down this code in the simulator and then try to run it. So whether it's compiled. So if you are completing, please upload your code in the chat window. Or So any question for this code? So even though it is a nested loop, the translation is not so different from the single loop, right? So you just specify the two loops in the code. Maybe you didn't know that J modulus 4 is simply you can translate to the end instruction. So that's the only different part. Okay, so I will give you this code as a homework. So you have to do it by yourself. So let us look at the next example. So which is containing the loop structure, like a while loop, and there's array, okay? So if array is there, how we can generate the code? Okay, so let's assume that this is integer type. Okay, so integer save, like 100, that is given. Okay, so then how we can generate the code? Okay, so the code is while for that int save some array, while save I is equal to k, then I plus equal 1. Okay, so we are trying to translate this code. Okay, so the array means this save is representing the starting address of that array. Okay, so how can you compute save I index? So that means it is save. Save is a location of starting point of the address. And we do not just simply add I, right? What do we have to do? We have to multiply of 4, right? Because one integer size is 4 byte, right? So address-wise, address is increased by 4, right? Because one address is corresponding to the 1 byte. For one integer, we need 4 bytes. So every integer, to access every integer, the address should be increased by 4, right? So we have to multiply by 4. Okay, so that is required. So we read data from the memory using the addresses save plus I multiply with 4. Okay, but we didn't know the multiplication operation yet. But this I multiply 4 is simply represented using some simple instruction. Which instruction do you have to use to do this multiplying of 4? Yeah, shift left logically by 2, right? 2-bit. 2-bit left shift, then it is multiplication of 4. So for this instruction, what do we do? Not that one. For this part, I multiplication 4, what do we do? We need shift left logically, and from, so assume that $1 is representing I, $2 is representing starting point of save. Okay, $3 is representing K. So let's assume that. Then shift left logically by 2-bit and storing to the some register. Okay, so that is $4 is representing I multiply 4. Okay, and then how we can compute save plus I multiply 4? That is, we need add instruction. So $2, $4, then $5. That is address. This is address. So which means that it is save plus I multiply 4. Okay. And then this operation is requiring the access to the memory. To access the memory, what operation, what instruction do you have to use? Yeah, load word, one word. What is address? Address is $5 and offset is 0 because $5 is actually representing the save I location, and that is stored into the some another register $6. Okay, so this 3 instruction is representing save I, right? So for this part, save array I, to specify this part, we need these 3 instructions. Okay, so the other part we can generate the first while loop. While loop case, we have to compare, right? We have to compare the condition, and then if the condition is satisfied, we are keep going to the loop. Otherwise, we have to go outside from the loop. So we are learning these 3 instructions, which is the save I, and then we are comparing to the K. Okay, so $6 is comparing the K. K is $3. Okay, then if it's true, then we have to go outside from the loop. So which instruction do you have to use? Branch equal, branch not equal. Which case do we have to leave from the loop? Yeah. Save I is different from the K, then we have to leave, right? So it is not equal, then we have to leave. Okay, no operation. Otherwise, we are increasing the I. So increasing I is add I, $1, $1. Okay, so increasing I. And it is the ending of the loop structure. So we have to go back to the original loop. So we have to go back to the loop, while loop. So loop is starting here, and no pressure. Exit is outside of this loop. Okay. So when you are translating the loop array structure, you just need to know that the type of array. So this is integer type. In that case, address is increased by 4. If this is like a character type, so like a character, save 100. In that case, we didn't need to increase address by 4. Character type case, the address is just only increased by 1. Okay, so that's the difference. So type should be considered. But anyway, you just thinking just only consider the integer type. Okay, so we are completing about the loop structure almost, right? A loop, an array. Okay. Okay, so then let's look at the basic block. What is basic block? We learn about the control jump or branch equal, branch not equal, jump instruction, right? So we learn about these 3 instructions. So then it's like this. There is add instruction, subtraction, and blah, 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 blah. And there is a jump instruction, branch equal instruction. So many instructions are mixed, right? So it's like this. Okay, so then there is some label here. Okay, like this. Okay, so when we are running this code, then it is sequentially executed, and this part, jump part, it is jumping to some place. So maybe this is jumping to something, and this is jumping to some other place, jumping to some other place. Okay, so then this is jump case is going go outside, and following this case, branch equal case, it can be go outside or it can be sequentially executed. Branch equal, it can be go outside or it can be sequentially executed. And here, loop, add instruction case. Add instruction case. There are 2 cases. Something is coming from the sequentially, or some jump instruction is going to this add instruction. There are 2 cases. And SSL is also, it can be reaching from the sequentially, where some another instruction is jumping to this X location. Okay, so by looking at the branch instruction, then we know that some part, so here this part, from add to the shift left. In this case, among this code, among this instruction, so from this one, if add is starting, then every instruction from add to add, subtraction, and the following instructions are executed, right? So it looks like one block. So what I mean is add, subtraction, and the following instructions are executed together always. Right? It's like so this is called basic block. SSL and instruction to J in this case. We cannot ensure that even SLL executed, we don't know add is executed, right? Because some another instruction is jumping to this SLL directly. In that case, we cannot guarantee the add instruction is executed. So this is different basic block. But we can guarantee that SLL is executed and J is also executed always. So it is one thing. And from here to this branch instruction, every instruction in this part are behavior as one block. So that is another basic block. Because when the first instruction is executed, then every instruction inside of here is executed. Okay. There is another block here. Okay, this is the basic block. So basic block case, the first instruction case, it can be executed from the sequentially or it can be jumped. So there is some label here. So somebody can jump that location. Okay. And among the page block, there is no jump instruction or branch instruction at all. And there is no label also. And in the last thing, there is some branch instruction. So it can be jump to some another place, or it can be going to the next. So among this part, we can guarantee that all instructions are behavior as one block. So that is called basic block. The importance of basic block is that, for instance, here there's add instruction, add $1, $2, $3. And there's another instruction, subtraction, $4, $5, $6. So let's assume that these two instructions belong to the same basic block. In this case, can you exchange the location of these two instructions? So is it okay? Instead of generating the code like this, what about this code? Subtraction, $4, $5, $6, and add $1, $2, $3. Is it okay or is it not okay? What do you think about it? Within a single basic block, if we are changing the instruction like this example, is it okay? Yeah, it's okay. Why? The register, destination register, is not used by another instruction, right? So these two instructions are using different registers. So they can be executed parallelly. Right? Concurrently, they can be executed. So in this case, we can change the order of instruction. Okay, so we can do the reorder of instructions in a basic block. If there is no dependence between these two instructions. Okay, so that means compiler is changing. Compiler change the order of instructions to optimize the performance, to improve. Okay, so within a single basic block, then we can arbitrarily change in the instructions unless they have dependency. Okay. But outside of basic block, we can't, because we cannot guarantee that the outside of instruction can be executed or not, right? So we cannot exchange it. So the basic block is very basic unit to be applied for the optimization in the compiler. Okay, so compiler is using this basic block. Okay, so here basic block is a sequence of instruction with no branch except at the end, and no branch target, so no label except at the beginning. So only in the beginning there will be label to be jumped to the location, and at the end there can be some branch instruction. So inside of that there is no branch instruction. So using that, the page plug compiler is identifying the page plugs for the optimization, and then compiler is a reordering of the instruction for each page plug. Okay. So we learn about the conditional operation, set less than, set on less than, set on less than I. So this instruction case, it is signed value. Okay, so everything is signed. But in some case, you are thinking that, okay, this register is should be interpreted as unsigned. So how can you do the unsigned? Let's look at later. Maybe, so we learn about this instruction, set less than, set on less than, and branch equal. So combining these things, we are implementing branch like less than, branch greater equal. So this can be interpreted as these two instructions. But maybe you are questioning about why there is no branch less than or branch greater than or equal to. Why there is no these instructions? Because if there is this instruction, then we can reduce the number of instructions, right? The reason is the implementation of comparison. So comparing is actually, we have to do subtraction. So subtraction means we have to add the addition, right? So we have to do addition operation. So we have to do, we will learn about the add operation, but add operation, multi-bit add takes a lot of times comparing with the simple equality check. So equality is much easier than computation. Okay, so branch equal, not equal is very simple instruction. Equal, not equal. For this instruction is much faster than that addition operation. Okay. Branch is very important instruction, so we'll learn about why the simple operation is only supported by this branch instruction in the chapter 4. So chapter 4, we'll learn about the detailed reason. So anyway, in the MIPS doesn't have branch greater than or less than, branch equal, not equal, branch greater than equal to. So those instructions not available. Okay. Signed and unsigned. So set on less than and set on less than immediate are supporting the signed comparison. So in some cases, you are interpreting the register as unsigned value. Okay, in that case, you have to change the instruction itself because register is just contain a binary. So the register doesn't representing this is unsigned value or signed value. We don't know that. Only through the instruction we can interpret. So set on less than unsigned. Set on less than unsigned immediate. This instruction is interpreting the each register and immediate value as unsigned value. Okay. So for instance here, $1 is 1, average is 1. So this value is in the signed value, what this value is representing. The signed value is -1, right? If it's unsigned value, then unsigned value, this is, how much is it? To the, sorry, 1 minus 1, maybe. So it's a very large number. It's the biggest number. Okay. So if we are comparing these two values, that less than, and then $0 is 0. $0 is comparing to $1 and result in the $2. Then what's the $2 value? Is 0 or 1? Set on less than. In this case, everything is interpreted as, so these two source register interpret as signed value. So signed value case, this is 0 and this is -1, less than is false. So this is 0. If set on less than unsigned, then what's the result? One. Similarly, set on less than immediate $2, $0, -1. Then $2 will be 0. 7 less than unsigned immediate $3, $0, -1. Even we are specifying the -1, but the instruction is interpreting the -1 as unsigned value, which is very large number. So $3 will be. So can you write this code in your simulator and then can you check really the register value is 0 and 1. And you can see that some error message, I think. Right? Because I think the simulator is not supporting this instruction, is not supported. Okay, because our simulator is not implemented this instruction. Maybe you can extend the simulator. So, anyway, so instead of that, instead of set understand, just specify add I three 0 -1 and then set on less than unsigned $4 $0 $3. Okay, can you run this code? So using these two instruction to replace settle less than unsigned immediate. Okay. So you can check, right? So is it working? So what's the rest value of $4? So can you specify $4 value in the chat window? Is it working? So currently, seven less than IU is not working. Okay. So now let's go to the. So next part is a procedure call, but we will look at the procedure call next time. Before that, let's look at the simulator, MIPS simulator. So somebody, maybe you want to change the simulator also, right? Or you want to run the simulator in your machine rather than through the website. So you have to go to the github.com and my account. And there is a simple MIPS. Okay, so can you go that location? I'm also writing that location in the chat window. Okay, then you can see that there is a simulator. This is simulator code. Okay. Here, seven less than IU is supported, but I need to check about that. So here, in order to change the code, actually source directory and the simulator directory has the same code. Okay, so it has a JavaScript file, and this is also same code. So you just need to change this code only. So only this simple mips.js, that is a JavaScript file. Okay, so to change the code, what you have to do is you have to download this whole code. Okay, so simply using this menu, download the menu. So through the git clone or just download the zip, then you can download the whole source code. Okay, and then in the simulator, you are running the functional.html file. Then you can see the simulator windows country you're using. Okay, and the simple mips.js JavaScript file opening. Then there are many instructions here. Okay, so from 250, so these are specifying the instructions. Okay, so these are support instructions. Okay, so set less than, less than. Maybe we can change the name here. Then it has this kind of format. So this part is, so I format case, this is OP code. OP code is 001011. That's the set on less than unsigned immediate. Okay, so this source code, source is 5-bit, RT is 5-bit, and immediate is 16-bit. This is format. Okay, so here you can add many instructions if it's missing. So it's supporting this logical operation. Multiplication, mul, and multiplication unsigned. It is source R type, and this is also R type. And branch instruction, branch equal, not equal. So even though it is supporting this instruction, but ignore this part. Okay, so ignoring this part. And this no operation, break, print, this is for the debugging. So this is not actual instruction, just for the debugging of your, so except no operation. This is the existing real instruction, but the other part is just for the debugging of your MIPS code. Okay, and these are really code. Okay, so immediate simulator mode. So here in the F step function. So if you are pressing the step, then this function is called. So whenever you're stepping, then it's looking at the OP code, which is 6-bit. So OP code is 0, that means it is R format instruction. Right? OP code is 0, then it's R format. R format case, which part do we have to look at? We have to look at the function part. Function 6-bit, last 6-bit, we have to look at. So 6-bit is 0, then it is shift 2 is a shift to right logically. So for every case, the instruction is defined. And here, 32 is add instruction, 33, add the unsigned instruction. So you can specify many instructions here. Even you can define your own instruction. Okay, so it's only using the 43. Okay, so function part is supporting the 60-bit, which means that you can support 64 instructions. 64 instruction of R format. So you can add more instruction here. Case 1, OP code is one case, is a branch instruction. And 2, jump instruction. We didn't know about this jump and link instruction. 4 is branch equal, not equal. Let's skip about that part. Add instruction, immediate part. So these instructions are specified. Okay, so if you are changing the simulator, then you can easily support many instructions. So if there is some missing instruction, then you can change that code. Okay, so that's the simulator part. So if you are learning this, the function, the HTML, after downloading it, then you can see these windows in your local machine. So currently it is supporting some website, but if you are downloading this code, then you can run the simulator in your local machine. Okay, so if you have any internet connection problem, then you can use the local machine code. Okay, so any question? Okay, for the midterm exam, I will announce in the next Monday the date. Okay. Next time we will continue about the function call and the MIPS. Okay. Okay. See you. Bye.